Yeah, no, thank you very much for the introduction. Thank you to the organizers for putting this all together. This is a really nice seminar series and sort of community that you guys are building, and I'm really, really happy to be a part of it. So as mentioned, I'm going to be talking about electroactive polymers, and so this is some joint work with Pradeep Sharma and Kosar Mosafari at the University of Houston. It also touches on some of my PhD work with Kaushik Dayal and another collaborator that I've been working with recently, Prashant Pirwit. So I'm going to try to touch on 3 different topics. The second one will be pretty brief, time permitting. But the 3 topics are going to be the flexoelectricity of elastomers and a multi-scale theory for that, and thinking about material design. I'll then move on to architected dielectric elastomers. I think that there are some interesting parallels between the 2 different types of materials. And we'll sort of finish on talking about Monte Carlo methods, and in particular focusing on the effects of dipole-dipole interactions within the material, and how that can lead to interesting collective behavior and some of the challenges associated with modeling that. So just some of the key takeaways that I hope to convey today is that if you look at the statistical mechanics of a single polymer chain in an electroactive polymer network, there's this really strong two-way coupling between the stretch of that chain and its electrical response, namely its polarization. And this leads to all kinds of interesting effects when you take these single chains and cross-link them in a network. It leads to some interesting electromechanical coupling, some stresses that occur, and we'll talk about some of those things. I want to convey the fact that polymer network architecture matters. We typically think of elastomer networks as sort of the chains being randomly distributed in every which direction, but I'll talk about ways in which you can design the microstructure to enhance the performance of the material. And then I'll talk about Monte Carlo methods, and as I said, some of the challenges. One of the principal challenges that when you have discrete symmetries in your thermodynamic system, this can really lead to some challenges in terms of the rate of convergence of Monte Carlo simulation. And I'll talk about how we've been addressing that. So starting off with flexoelectricity. Flexoelectricity is the coupling between electrical polarization and strain gradients. In soft materials, flexoelectricity has a lot of really exciting and interesting applications. So people have thought about using flexoelectric soft materials to harvest energy. If you have sort of a periodic bending motion that's occurring, then you can use that to generate some electricity. People are also really interested in using these kinds of materials for soft biologically inspired robotics, like this gripper here on the right, or this robotic octopus down here in the bottom left. And also, integrating soft materials, electronics, and sort of everyday life and wearable sensors and electronics. So, but it turns out that our multiscale understanding of flexoelectricity for elastomers was sort of incomplete. But we had a very good understanding of crystalline materials, and there's a nice clean picture here. So I think it's good to start by just briefly describing why we see the flexoelectric effect in crystalline materials. And the way that I like to understand this is in the following way. So if we have a crystalline lattice, we maybe have some particles that are arranged in a lattice that are maybe weakly ionic. They maybe have some net positive or negative charge. And now if we think about sort of relating the deformation gradient at a material point to how the lattice vectors are changing under that deformation, what's very often used is what's called the Cauchy-Bom rule, which is essentially that each of the lattice vectors is mapped under the deformation gradient. What you see when you do this is that you need to have a strain gradient. As long as you have a vanishing dipole moment in the reference configuration, you will always have a vanishing dipole moment in the deformed configuration as long as your deformation is homogeneous. And so this means that piezoelectricity is really something special. You need to sort of break symmetry in some way, or your material needs to be violating the Cauchy-Bom rule in some weird way. But you know, it's pretty easy to fix this by allowing each of the lattice vectors to map under a slightly different deformation gradient. So if we have a strain gradient, if F is changing in space, then we can now this can now give rise to a net dipole moment, a net polarization within the crystalline material. Okay, and so I think that's a nice clean picture of piezoelectricity and flexoelectricity in crystalline materials. But what about elastomers? It turns out that elastomers, at least at first glance, are a bit more complicated, because if you think about the microstructure, these are really a collection of these long spaghetti-like macromolecules that are fluctuating about all over the place. And so sort of the position is not of a given monomer, a given particle within this microstructure, is not very well described by some mean. Things are fluctuating all over the place. But it does turn out that even though there are a lot of fluctuations that we need to consider, the end-to-end vector, that is the vector that connects the beginning of a chain to the end of a single chain within this network, this does actually have a very nice analog of the Cauchy-Bom rule, which is people often make this affine deformation assumption. They assume that the end-to-end vector, even though we can't say things about the individual atomic positions, we say that the end-to-end vector maps under F. Okay, and so now starting off with this affine deformation assumption, let's build a multiscale model. And roughly speaking, what we're going to do is we're going to start off by considering the statistical mechanics of a single chain. So we're going to average over the thermal fluctuations and get its electromechanical response. And then we'll take a unit cell and we'll average over the chains in this unit cell. And so for our chain scale mechanical model, essentially what the model that we use here is the freely jointed chain. So here we have monomers that are joined together end to end. We assume that the monomers themselves are rigid, so the monomers don't deform, but that they are free to rotate about their neighboring bonds. And so sort of all of the deformation occurs by monomers rotating relative to each other within the chain. And then, so that's sort of the mechanical side of things. On the electrical side of things, we assume that there is some dipole that is rigidly attached to each monomer. And so if the monomer direction is n hat, then I say its dipole is some rotation matrix applied to n hat. And so the upshot of this is that we can solve the statistical mechanics problem. We can get the free energy sort of as a function of the end-to-end vector and an applied electric field. And we can understand things about the sort of the stress and the mechanical response of a single chain. But what's really important, what's really interesting, is that we have this very simple relationship that emerges for the electrical response of the chain. And that is that the electrical response of the chain, it's net dipole. So if you take each of those individual dipoles, you average them over thermal fluctuations, and you think about what the net polarization is. It's simply that linear transformation, that rotation matrix applied to the end-to-end vector. And then this is just a correction for length. Oh, and times the dipole magnitude. I apologize. So this rotation matrix actually has the yeah. So it's not it's the dipole magnitude times a rotation matrix. Excuse me. That's what M is. So the dipole magnitude is baked into this tensor M. And so now if you have this and you consider a simple example, so let's assume that M is the identity, and so the dipole is aligned with the monomer direction. And now I take a unit cell This is a very common unit cell to assume in elastomer networks. Here we have 8 chains which are joined together at the middle of this unit cell, and sort of each of the chains are emanating out to one of the corners of this cube. And so here in the reference configuration, even though each of the individual chains has some amount of polarization, it's easy to see that at the continuum scale, the polarization is vanishing because there's a sort of an equal and opposite contribution for each of the chains in this unit cell. But you can sort of easily see that once you take this unit cell and you bend it in some way, so we have a strain gradient going in the vertical direction. We are sort of stretching the bottom of this unit cell more than we are the top, relatively speaking. And what you see when you do that is that we are very much decreasing the contribution of the polarization in the bottom half of the unit cell. Its sort of downward contribution is much less than it was in the reference configuration, and we're slightly increasing the contribution of the polarization in the strain gradient direction for the top half of the unit cell. And what happens is that you now have an induced polarization, and now you have a multi-scale mechanism, sort of a multi-scale understanding of why flexoelectricity occurs in elastomer networks. And so it turns out, of course, there are equations that go with this. Here, if we assume this simple form where I have principal stretches in the E1 and E2 direction, and those are sort of varying with respect to the E3 direction, that we can get a precise expression for what we expect the flexoelectric effect, flexoelectric coefficient to be. What's super interesting, and we didn't realize this until after the fact. What's super interesting is that the equations agree with this very surprising experimental result, which is that if you take a lot of these elastomers and you stretch them in the strain gradient direction before you measure, you stretch them in a strain gradient direction, you apply the strain gradient, and then you measure the flexoelectric effect. What you find is that this can lead to a very, very large increase in the coefficient of flexoelectricity, very large increase in this coupling. And for a while, this was not, people didn't really know how to explain this, but it turns out that this comes out very simply from our theory and from our equations. So we're happy to see this. We've also, thought about the problem of material design as well. So if instead of thinking about a unit cell with randomly oriented chains, instead, what if we introduce some order into the material? And in particular, if we think about pulling the chains, by pulling I just mean having the chains have some preferred alignment in a particular direction. So in this case, it's in the vertical direction. We have the chains, it's sort of in the bottom half of the unit cell with their polarization pointing in the vertical direction, and in the top half pointing in the vertical direction. What we see is that we can actually design a material that now exhibits piezoelectricity. And what's interesting is that there's sort of this trade-off. You can enhance the piezoelectricity, but it's at the expense of the flexoelectric effect. There's no free lunch here. And we can push this a bit farther. So we can instead think about specifying the directions of the dipoles along the chains for each of the 8 chains in the unit cell. Here there's really only one restriction, and that is we're applying this inversion symmetry. So sort of the blue chains have the same dipole direction, the red chains have the same dipole direction. And this just leads to a material with a vanishing net polarization in the reference configuration in the interest of material stability. But anyway, what you find when you do this is that you can now think about tuning the direction of the induced polarization with respect to the strain gradient in various directions, and enhance the flexoelectric effect in different ways. So this was quite interesting as well. Okay, and so I'll fly through this next part because I really want to. I see I have about 4 or 5 minutes left, and I really want to move on to Monte Carlo methods and some of the interesting things that we see there. But anyway, the electrical model that I had presented before, where we simply had a dipole rigidly attached to each of the monomers, that's not the only electrical response that you can have. That's sort of the most simple one. But another electrical response that we've been thinking about is this idea of now dielectric monomers. So monomers which do not have a dipole ordinarily, but will form a dipole in response to an electric field. You can almost think about, these monomers as having some electron cloud, and when you apply an electric field that pushes this electron cloud in a certain direction, such that we now have a net positive charge on one end of the monomer and a net negative charge on the other end of the monomer. And so you can see some interesting things when you solve the statistical mechanics problem here. One in particular is that the polarization response of a single chain can often be misaligned with the electric field direction. And that leads to an electrostatic torque because the chain wants its polarization to be aligned with the electric field. And so you actually get some stress and some torque that develops in the chain itself, just as in response to the applied electric field. And you can also think about what that means in terms of the material design. So here, what we did is we thought about, instead of having chains randomly, thinking about the importance of how the chain is, its orientation with respect to the electric field. Thinking about that and really using that as inspiration, we thought about, okay, well now, what if instead of having chains randomly oriented in every which direction in our network, instead, what if we had some preferred directions where there was more chains oriented, and some less preferred directions where there are less chains oriented? And that's sort of what I'm trying to show with these spheres. The red regions maybe have a higher density of chains, the blue regions a lower density. And sort of the punchline here is that you can really enhance the amount of actuation per applied voltage that you can get out of these materials by tuning the microstructure in this way. So anyway, with the last couple of minutes, I want to talk about Monte Carlo methods. I think that I'm particularly excited about this because it really has the potential. Sort of everything that I have presented up until now has been in the regime of sort of negligible dipole-dipole interactions. I mean, it turns out, analytically, solving the problem where you have long-range interactions between all of the atoms in your system is a very, very difficult thing to do. And so we're going to turn to Monte Carlo methods here in order to try to understand the effects of interactions and some of the collective behavior that can emerge. So just a one-slide crash course on Monte Carlo for anybody who is not familiar. The basic idea here is we use random sampling to approximate ensemble averages. And so instead of performing exact integration to get to average over thermal fluctuations, now we're going to use random sampling to try to approximate that. In particular, we're going to use Markov chain Monte Carlo, which means that each new random sample is a perturbation, some kind of perturbation of the previous example. And the idea here is that it sort of roughly mimics thermal fluctuations. You're kicking the system around randomly just a little bit from its current configuration, with the idea being that you will explore the most important parts of configuration space. And so why Monte Carlo? Well, Monte Carlo mitigates this curse of dimensionality. I mean, it turns out that integrating in, and I'm sure this is well known to everybody here, but just to make it explicit, integrating in a high dimensional space is really, really prohibitively expensive to do using quadrature rules. But Monte Carlo still performs well in higher dimensions. And so this is all great, but the crux of the problem here is that we need to have a good choice of a good choice for how we perturb our system, for how we generate the next sample, next random sample. And so I see him at 21 minutes. Let me just quickly try to explain the core idea here. What we find with the dielectric monomers in particular is that if we have a monomer aligned with the electric field and we have a monomer that is in the opposite direction of the electric field, these have a very similar energy. But there is an energy barrier between them. So sort of being aligned with the electric field or being the opposite direction of the electric field, these both have a high probability of occurring because they're low energy states, but it's very unlikely to have some sort of intermediate state. And so we might think to ourselves, well, okay, if we want to generate our next random sample, one thing that we can do is we can start randomly flipping monomers such that they're in the opposite direction, or that we reflect the monomer directions in the plane orthogonal to the electric field, something of that nature. But the issue here is that neighbors want to align. So if I pick out one particular monomer and I try to flip it, I go from this case, which is very nice and energetically favorable. This is very low energy, so I have positive charges next to negative charges. If I try to take sort of this top one and flip it, now I'm putting positive charges next to positive charges, and negative charges is bad. It's a very high energy state. And so something that has been a bit of a breakthrough with this problem recently is this idea of now using clustering, which is sort of a classical idea in Monte Carlo methods, but has not been applied to this particular problem. So because it's so difficult to flip one neighbor when two monomers are aligned, because it's so difficult to flip one of them and not the other, we pick out a sort of a chunk of the chain in which monomers are roughly aligned with each other, and where at the boundary the monomers are roughly orthogonal to each other. And it turns out that we can make this flip without much of a change in the energy. And so this state is roughly as likely as the previous state. And so this ends up being a very nice way to sample things and get a sense of what the effect of interactions are within these materials. And so one of the reasons why, and this is one of my last slides, but one of the reasons why I'm so interested in interactions is because I would like to get an understanding of whether or not electrically induced phase transitions can happen within the material. And if we can use this to enhance the electromechanical coupling through phase transitions. And so this is a very simple result, preliminary result, where we're looking at I have the force on the end of the chain on the x-axis, the stretch on the y-axis, and now I'm looking at this force stretch curve as a function of different applied electric fields. And the punchline here is that once you have reached a certain threshold for your electric field, the stiffness of the chain almost vanishes. And so this sort of looks like perhaps the onset of a phase transition. But this is still, this in particular is still work in progress. And so I mentioned this before, but this has connections to, and it's very much inspired by clustering in the classical Ising model. Right. And so, yes, I'll quickly conclude. We talked about, multiscale theory for flexoelectricity in elastomers. Very briefly talked about dielectric elastomers. We thought about material design in either case, and briefly talked about some new ideas for Monte Carlo methods. And yeah, so with that, I'm happy to answer any questions.